part you want to make. Then you're going to bring that model into a slicing software, which is going to prepare the model for printing and generate some machine instructions for the 3D printer. And then finally, you're going to send those instructions to the 3D printer and kick off a print. Now, those steps are the same across most 3D printing processes, and this is actually a great graphic from our friends at 3D Hubs. There's a wide landscape of different 3D printing technologies out there, and I think in this graphic here, there's about 15 different types it's showing, 15 different types of processes. We're going to talk today, though, specifically about material extrusion and extrusion-based 3D printing, which is one half of the two processes that Markforged uses to produce the strongest parts in this category. So extrusion-based 3D printing at its core is kind of like a precision hot glue gun. It's called fused filament fabrication, or FFF sometimes. But you're basically taking a plastic filament feedstock and you're melting it through a nozzle and you're laying it and using that to produce a part layer by layer, one layer at a time. So what that looks like, and I'm going to use this example of a end effector a couple times today. You're going to have this end effector, this gripper jaw in CAD. You'll export that as an STL, and then you're going to slice it. And slicing is kind of similar to slicing some deli meat. It's going to cut that model into a bunch of really fine, thin layers. And as part of the slicing software, you'll also choose your part orientation in your printer, as well as configure some material characteristics of that part. And finally, that model is going to be then divided into thin layers and generate machine code to tell the printer what to do. So a slicer will take a part geometry like this gripper right here, and it's going to slice it into a bunch of different thin layers. And the end part will look something like this, where it's a bunch of different layers built up to produce that final part. To give you a sort of comparison to CNC machining requires you to do CAM, or computer-aided machining toolpaths. So you have to basically program the toolpaths that your cutting tools are going to take to produce your part. Well, 3D printing is a lot easier. It requires slicing, but the sort of CAM of 3D printing or slicing is all done automatically by 3D printing software. Now, this is the plastic side of 3D printing. So Markforged uses two processes. We've talked about FFF. We also have a process that we developed called continuous filament fabrication, which is how we add high-strength, continuous composite filaments to our parts and make them really strong. So very similar to a more traditional 3D printing process, you're still going to design your part in your favorite CAD package and model your part. You're then going to bring it into Markforged's software called Eiger, where you're actually going to also select reinforcements. You're going to actually choose where you can actually put really high-strength composite fiber into your parts. And that's going to allow you to get really high-strength parts up to about the strength of aluminum. And then finally, you'll send that file off to your printer and allow it to print and produce a part. But to give you an idea of what that process looks like, I'm going to actually look at this actual gripper in practice. So this is also from our friends at Dixon Valve, and it's a three-jaw coupling, or it's a three-jaw gripper that grips a pipe coupling. You can kind of see it in action right here as it grips that coupling. So that jaw in CAD looks like this. And for purposes of explanation, because 3D printing software slices apart layer by layer, I'm going to look at specifically this layer in the CAD. So I've done a cutaway here to show you that. Now, I'm going to look at this head on. And so this is the cross-section of that layer, or cross-section of that part in CAD. And this is what Eiger, our Markforged software Eiger, is going to do to slice that part and produce tool paths. So what you can see here is we actually produce a sparse honeycomb infill in those parts. So the white toolpaths you see here are our onyx material, which is a chopped carbon fiber nylon blend. So we have a nice sparse infill. And then on the outer shell of this part, we're laying down a continuous strand of composite fiber to add a lot more strength. And when the printer actually produces that, it looks like this right here. And so you can actually see, believe this is Kevlar right here, that's running all the way around the outer shell of that part to add a lot of high strength to this gripper jaw. And what that looks like on the printer, this is on our Mark II, is that right there. So that at that layer, we've added continuous composite Kevlar all the way through that part. So we've talked about how Markforged makes these really high strength parts with both our plastics and composites material. But I want to also show you how easy the process is to design a end of arm tool and then have it printing in as little as 15 minutes. So I'm starting with a standard template tool. And this is something that, it might take you a few minutes to a half hour or an hour to design the first time. But every time you need to make a new tool based on this template, you can just start with the template every time and save a lot of time each time you design a new tool. So I've designed this template tool already, and this goes with a Schunk gripper jaw, or for a gripper. And I'm going to then import my part that's going to be manipulated. So in this case, it's this pipe coupling you see here. And I've positioned that pipe coupling in relation to where I want the gripper to actually grip it. But you can see that there's a bit of interference as that coupling is actually located inside the jaw right now. And that's okay, because that's where our Boolean operation comes in. So now that I've correctly located this pipe coupling in relation to where I want it to be gripped by the gripper, I'm simply going to run a Boolean operation and subtract the geometry of that pipe coupling from the gripper jaw. Once that's done, and it's 3 clicks to finish, I'll do a little bit of cleanup operation. So I kind of subtracted away a little bit of the faces and geometry that was left over after that Boolean operation and clean this up. So at this point, we have the geometry and the design for a really nice conformal gripper. The only thing I want to do now is to just make this a little bit more environmentally friendly for humans to handle. There's a few sharp edges right there, so I'm going to add just a few quick fillets. And I'm also going to add actually a couple cutaways for myself to insert some steel machine keys. So one of the things a lot of times these, for instance, a coupling like this might be casted. So you may be worried about the casted surface finish wearing away this gripper. So in order to add some wear resistance and extend the lifetime of this gripper, I've added these square cutouts for a machine key, and I'm going to press them in, or press a machine key into those voids there. And now I've had a really strong wear resistant surface to my gripper as well. And so at this point, our design's pretty much done. And you can see that this would be, 2 of these grippers would be used to pick up this coupling you see here. So at that point, we're good to go, and we can export that geometry as an STL and bring it into Markforge's software. And from here, we're going to choose a couple quick options to choose our materials, and then we can just hit print and send that off to the printer. And so when it comes down to it, once you've designed and developed a couple template jaws or template tools that you use pretty often, or fit the geometries of parts that you're often gripping, it's really easy to quickly do a Boolean operation, subtract away that part from the jaw you're trying to print, clean it up a little bit, and then send it off to the printer. So to wrap this up today, I want to share with you a challenge that a customer of mine, the guys at Dixon Valve, posed to me to help them redesign some tooling for a automated assembly cell that they had designed. So to give a little more explanation of this, I want to show you a short video of this robot arm in action. So the printed end effector jaws are going to pick up a pipe coupling and also a polymer ring. They're going to then drop the ring and then the pipe coupling on this rotary table in one of the set positions here. The robot's then going to pick off one of the couplings that's already finished from this table, and it's going to drop it in the output side of the machine. In the back, you'll see that jaw get pressed, or the coupling be pressed into the polymer ring, and then it goes back and repeats the process. And this is a automation cell that significantly accelerates the assembly step of this pipe coupling. So as you can see, the assembly cell worked, but one of the issues with it, and the one specifically that they were asking me to help with, was that over the course of gripping these pipe couplings, and the jaws are basically going into the pipe coupling and gripping against a sharp threaded surface, as you can kind of see here, the contact surface of those jaws was wearing against those threads. And you can kind of see the wear here, as I'm indicating by the arrow. And what they were finding was that the jaws really had about a 1 month preventative maintenance schedule. So they really had to swap them out basically once a month due to this wear. And so they liked the ability to iterate quickly on new tooling and